Hello all. In this lecture, I'll tell you about Couette Flow. So this is basically a class of a parallel flow, and you know what the parallel flow is, that only existing velocity is in the direction of flow, and rest in the rest directions the velocity is zero. So what is Couette flow? It is a flow between two parallel plates such that one plate is fixed and the other plate moves with a constant velocity, let's say u infinity, and the flow field is generated between them, and the fluid is flowing from left to right. So now, to solve this problem, we have to have some assumptions. The first assumption is of parallel flow. Now, another assumption is that the flow field is steady. That means the temporal variation of the hydrodynamic and thermodynamic properties do not exist. Then it is laminar, and then it is fully developed. What is fully developed flow? Fully developed means that everywhere the influence of viscosity is there. That means the order of Reynolds number, and or in other words, the order of viscous forces and inertia forces is same everywhere in the flow. So everywhere in the flow, the influence of viscosity is there. So it is steady, laminar, fully developed, and no body force, let's say. That means the spacing is very small. And one important assumption is that z direction, the width of plates is huge. So what does this particular assumption do? As the width is very large in comparison to the direction of flow, the variation of any property will cease to be the function of z. Why? Because the z direction is huge. So with these assumptions, let us start with the first thing. Remember, in the previous lecture, I have only showed you the momentum equation. But Navier-Stokes equation also comprises the mass conservation, because you have to solve mass conservation in priority. So what is that? In the Cartesian coordinate system, the mass conservation is del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w, and that is equal to 0. Now, as the problem is steady, so this will vanish. Apart from this, due to and one more assumption is there, very important assumption, incompressible. That means the density doesn't change. So the moment you say incompressible, rho will come out, and as rho can't be 0, so this equation will simply get reduced to del u by del x, del v by del y plus del w by del z, and that is equal to 0. Friends, as this is a parallel flow, so v and w will be 0. So their changes will also be 0. So here you came to a very important conclusion that del u by del x is equal to 0. That means the velocity, the only existing velocity which is in the x direction, is independent of the direction itself. So on what this u will depend? So this u can either depend on z or on y, but we have also assumed that the width of plate in the z direction is huge, is very large. Then that means that any let's say phi is any property. So phi, if this is a property in this particular problem, then that will no more be the function of z. So how come u will be the function of z? So z will not come into picture. So therefore, the conclusion which you draw from the continuity equation is that the only existing velocity, that is u, will be the function of y, and that is what the role of continuity equation in this analysis. Now comes your y and z momentum equation. So let us see. So v is 0. Okay. Now the moment v becomes 0, the whole acceleration terms become 0. There is no body force. V is 0. So what has happened to our momentum equation in y direction? It has simply get reduced to del p by del y is equal to 0. Similarly, for the z direction also, you came to a conclusion that del p by del z is equal to 0. Aha! P is neither function of y nor function of z. So P must be the function of x. This is a very, very, very important conclusion. So P is neither the function of y nor the function of x, so z, so it has to be the function of x. And this becomes what? If let's say initially P was function of dx, dy, dz, then what is dp? It will be nothing but del p by del x dx, del p by del y dy, del p by del z dz. But here we are saying that p is not a function of z, so this will vanish. P is not a function of y, this will also vanish. So what has now left? It is dp is this, so we can simply say del p by del x can be written as dp by dx. The same thing we could have also said here, that del u by del y will be nothing but du by dy. In the same, if you use the same analogy, you will be getting this. Now comes our x momentum equation. So if you look this equation, that problem is steady, okay. U is not 0, but variation of u with respect to x is 0. Look here. From the continuity, we came to a conclusion that u doesn't vary with respect to x. This. Okay. Now v is 0, w is 0, no body force. Here, in this Laplacian term, that u is not a function of z, u is not a function of x as well. So this whole Navier-Stokes equation has converted into 0 minus del p by del x plus mu del 2u by del y2. Very simple. So if you slightly solve this, you will be getting this. But p is a function of x only and u is a function of y only. So this partial derivative will get converted into ordinary derivative. Now you can very well appreciate the fact, friends, that the parallel flows with other assumption has led to solve us this humongous looking task of solving Navier-Stokes, because these assumptions for the flow, that is Couette flow, has led us to this particular differential equation, which is an ordinary differential equation and very easy to solve. Now, why it is very easy to solve? Right hand side is a what? Is a pressure term. Left hand side is a velocity term. Already you have seen that u is solely a function of y, and you have also seen that p is solely a function of x. So if p is solely a function of x, then its derivative can be either then its derivative can be either a function of x only or a constant. Similarly, as u is a function of y, so its derivative as well as second derivative can either be a function of y or a constant. But this is a derivative of y, this is a derivative of x. So in what condition they will be equal? Only and only when this or this is a constant. So therefore, d2u by dy2 will be 1 by mu dp by dx, and this is nothing but a constant. So the right hand side will be acting as a constant. So now if you try to solve this differential equation, so you just integrate it. So del 2u or d2u by dy2 dy is equal to 1 by mu dp by dx. Now this is a constant. So dy, then a constant of proportionality will come, let's say c1. So what will happen to this? This will simply becomes du by dy is 1 by mu dp by dx, and this is what? Y. Again, if you try to solve this, so this will be integral du dy integrating with respect to y is 1 by mu dp by dx. This whole is a constant, so it is y dy plus integration of c1. C1 is a constant, so I can do what? I can bring this c outside. So this is c1, and then this is dy, and then again an integration constant. So this will simply becomes u, and this is y square by 2. So I can write this thing as 1 upon 2 mu dp by dx, and then y square, then c1y, and then c2. Now I have to solve this, then I should have some boundary conditions. So what are those? So if you look this particular problem, so here at the bottom the velocity will be the velocity of the plate, and what is the velocity of the plate? It is 0. So the velocity of the fluid very adjacent to plate, that means when y is equal to 0 will be 0 only, and this is what we call as no slip boundary condition. Whereas if you look this particular plate, this plate is being dragged with a velocity u infinity. So the fluid layer which is in immediate vicinity to this particular plate will also be having the velocity of the plate. That means the relative velocity between the fluid and the solid at the solid surface should be 0. No slip boundary condition. So the velocity when y is equal to, let's say, the spacing between the plates is h. So when y is equal to h, the velocity is nothing but the plate velocity, and when y is equal to 0, the velocity is 0. Both are what? No slip boundary conditions. So let us write again. So when y is equal to 0, the velocity is 0, and when y is equal to h, the velocity is the velocity of the plate. So if we replace first one, so 0 is 1 by 2 mu dp by dx into 0 square plus c1 into 0 plus c2. So from here, this is 0, this is 0. So we came to a conclusion that c2 is equal to 0. If we replace the second boundary condition here, so you will be getting u infinity 1 by 2 mu dp by dx. This y will become h. It is c1 h plus c2, but c2 is 0. So from here I can write c1 as u infinity minus 1 by 2 mu dp by dx h square, and then whole 1 by h. Or you can bring this thing inside. So this will be u infinity by h minus 1 by 2 mu dp by dx into h. Now replace the value of c1 in this equation and c2 as well. So you should be getting now u as 1 by 2 mu dp by dx y square plus c1. C1 is u infinity by h, and minus 1 by 2 mu dp by dx h, and there is one y. Okay, now you try to solve this. It is 1 by 2 mu dp by dx y square plus u infinity into y by h minus 1 by 2 mu dp by dx hy. So now what you do is you club these two, or you bring these two terms together, and we will be writing this term first. So it is u infinity y by h. Let us take 1 by 2 mu dp by dx common. So this will becomes y square minus h and then y. Okay. So, we should not have removed this h square, so it doesn't matter. So what we'll do is we will write this h as h square by h. Okay, and now we'll take this h square outside. So this will become u infinity y by h 1 by 2 mu dp by dx, and we have taken this h square outside. So this is h square, and this will be y square by h square minus y by h. Again, we will take minus y by h outside. So this will become u infinity y by h plus h square by 2 mu. We have taken minus, so we'll club this with dp by dx, and then it is 1 minus y by h, as we have taken negative also out, so it is y by h. Now you divide the whole equation by u infinity so that it becomes non-dimensional. So u by u infinity is y by h plus h square by 2 mu u infinity minus dp by dx times y by h into 1 minus y by h. Friends, this is an expression for the velocity profile in case of Couette flow. So now, if you slightly solve this or consider this term as alpha. What is alpha? Alpha is nothing but h square by 2 mu u infinity minus dp by dx. Now in this whole equation, everything is non-dimensional, so this has to be non-dimensional, and this is what we call as non-dimensional pressure gradient. And there is a special purpose of keeping negative inside here, because in the direction of flow, the flow is happening from left to right. So flow is happening from left to right. So the pressure downstream has to be less than the pressure upstream. So that will result in a negative pressure gradient. So that negative pressure gradient will make this alpha positive. Okay. So now the velocity profile will be u by u infinity y by h plus alpha y by h 1 minus y by h. Friends, this is the complete velocity profile in case of Couette flow, and this alpha is having a very special role to play when it comes to Couette flow. You know why? Let me show this to you. When alpha becomes 0, this whole term will become 0, and velocity variation will simply be a linear equation like this. So if these are the plates, then here velocity will be 0, but here it will increase linearly. So this is for alpha is equal to 0, and it will attain the velocity of the plate. So here this will be nothing but u infinity. Now when alpha becomes 1, when alpha becomes 1, this is minus y. So this is what? This will increase and attains a maximum value here again. But here the slope will also be 0. Why? Let us see. So when alpha will be equal to, let's say, 1, okay, or before that, what we'll do is we'll try to differentiate this. So it is 1 by u infinity du by dy. So this will come out as 1 by h plus alpha, and this will go inside, so it is 1 by h and minus 2 uh, y by h square. Okay, so friends, when alpha becomes equal to 1, this equation 1 by u infinity du by dy will be equal to 1 by h plus alpha is 1, so it is 1 by h minus uh, so we are where we are at the place when y is equal to h. Okay, so it is minus 2h by h square. So this will becomes 2 by h minus 2 by h, which is nothing but 0. So here at this point the slope becomes 0. So for alpha is equal to 1, the profile will be like this, and here this will be the value u infinity, but it is the slope which is also 0. And when alpha becomes more than 1, so the slope will get converted into this. So the maximum value will be slightly below this, and this is for, let's say, this is for alpha is equal to 1, and this will be for alpha is equal to, let's say, 2. Okay. Now, friends, when alpha is equal to minus 1, what will happen? When alpha is equal to minus 1, okay, when alpha is equal to minus 1, then this will be what? This will be 1 by u infinity du by dy, and this is 1 by h minus 1 by h plus 2y by h square. Now, let us try to understand what is the slope when y is equal to 0 for alpha is equal to minus 1. So, when y is equal to 0, when y is equal to 0, du by dy will become 0 because this term becomes 0 and this will get cancelled out. So, therefore, for alpha is equal to minus 1, the slope will be 0 and then it will increase like this. So, this is alpha is equal to minus 1. So, now you can very well appreciate the fact this is on the verge of separation. Why? When alpha I decrease further from, let's say, alpha is minus 1 to minus 2. So, this will be the case, friends. That is alpha is equal to minus 2. And here you can see the flow velocity is to the left. Okay. So, why? Because alpha is nothing but having this pressure gradient. When alpha is positive means pressure gradient is negative, that means favorable pressure gradient, and the flow should happen from left to right without any problem. But the moment when alpha becomes equal to negative or minus 1, doesn't matter, minus 1 or minus, or let's say minus 1. So what is happening, this term is becoming positive, so pressure gradient is becoming positive, and when alpha is minus 1 means, that means it is on the verge of separation, and when alpha becomes minus 2, minus 3 and so on, this becomes such a huge value that on the, at the boundary it try to separate, not only try, it separates itself, and hence the flow becomes moving from right to left rather than left to right at the boundary, which is fixed one. So that's why the knowledge and the choice of alpha is so important when it comes to Couette flow. And in this lecture, till this point only, in the next lecture, we'll try to learn about different type of flow, which is called as plane Poiseuille flow. And again, that is one of the class which is also known as parallel flow. Thank you very much.